Welcome. In this session in linear data analysis, we'll use some simple linear algebra to connect the confusion matrix to the receiver operator characteristic, or ROC. Now let's re-examine the confusion matrix. The usual way is what we could call absolute terms. And in absolute terms, what we have is a confusion matrix that will continue, these are our labels, so that's +1, -1, these are our classes, so that's +1, -1, and the usual way is we put in the number of true positives here, the number of true negatives here, the number of false negatives here, and the number of false positives here, and then this row sum is the number of positives in a label set, and this row sum is the number of negatives. Now, we could also put this as relative. And if we put this as relative, this is the picture we would get. We would have +1 and -1 as our classes, and we would have +1 and -1 as our labels. And now, instead of putting the true positives, let's put in the true positive rate, which is the true positives divided by the positives. So let's make that the true positive rate. Let's make this the true negative rate. Let's make this the false negative rate. And let's make this the false positive rate. And now, let's consider what the row sums would be. Well, if I take the true positives plus the true false negatives, that's P. If I divide those by P, then that row sum has to work out to be 1. And similarly, if I've taken the false positive rate is false positives over negatives, and then I add the true negative rate, which is true negatives over negatives, that will be n over n, and so that also has to be equal to 1. What we have here is an interesting situation. So we have 4 entries in the relative, in both the absolute and the relative table. But in the relative table, we have 2 constraints. And that implies that we have only 2 degrees of freedom. Now, in the absolute table, we have 4 degrees of freedom because these are absolute numbers. Once we've converted to a relative, we've put the constraint that these have to equal 1, so we've only got 2 degrees of freedom. That is, if you give me one of the values in the first row, I can calculate the second one, and if you give me either of the values in the second row, I can calculate the other one. So there are 2 variables. So for our 2 variables, what we'll use the true positive rate and the false positive rate. And now let's make an observation. When we had the absolute confusion matrix, it takes 4 variables to represent it. When we have a relative confusion matrix, it only takes 2 variables. And 2 variables can be plotted in 2 dimensions. So that is where we're going to go. We're going to compute a relative confusion matrix, and then we're going to take 2 of the entries, and we'll just pick these 2 in the first column, and we can then make a plot, and a dot on a plot will represent the entire relative confusion matrix. So what we then have is the receiver operator characteristic is a 2D measure. And we can represent that as a pair, which is the false positive rate by convention usually comes first, and then the true positive rate by convention comes second. And now what we can do is we can then represent this in a plot. And in that plot, what we would have is this would be the false positive rate. And this would be the true positive rate. And the false positive rate goes from 0 to 1, and the true positive rate also goes from 0 to 1. So this is a unit square. And now what we can do is we can represent an entire confusion matrix as being a point within this unit square. And if we vary a threshold, a hyperparameter theta, we might get a different confusion matrix, as you did in the previous session. We could get a different confusion matrix for every setting of a hyperparameter. And so what we would be able to do is we would then be able to plot these. And if it was continuous, we would draw a curve. And as we draw that curve, this is referred to as the ROC curve. And what the ROC curve means is that any point on the curve specifies a relative confusion matrix, and any relative confusion matrix specifies a point on an ROC curve. Let's explore some data that I derived from an article that we refer to in the accompanying notes for this lecture. In this, the author supposed that there were 5 classifiers working on a single data set. These are ROC points. That is, each one of these points represents a false positive rate and true positive rate that are a confusion matrix from which we can completely compute a relative confusion matrix for the classifier. Here, the author wants to draw our attention to 5 of them. This is a pretty good classifier, number A. That is, it has a low false positive rate and a moderately high true positive rate. This is exactly on the dividing line for a random classifier. That is, this performs about as well as chance. This performs better. That is, it has a modest false positive rate and a fairly high true positive rate. This is an extraordinarily good classifier. Its false positive rate is nearly 0, and its true positive rate is nearly 1. This is a classifier that's performing at worse than chance. It has a higher false positive rate than it does a true positive rate. So these are examples that we can draw from the data. The author also presents us with scores and asks us to go through a problem in which we vary a hyperparameter by 20 values. And when we do, this is what we get, is we see that it starts out at one hyperparameter value, it's got 0, 0 basically, and then as we change the parameter, this as a discrete function increases until finally we arrive here. So a very common observation in classifiers is that by the time we have a false positive rate of 1, that is, by the time we've correctly classified everything, we also have a false positive rate. Sorry, by the time we get a high true positive rate, we often have a very high false positive rate. So this diagonal is representing, you can think of it either as the null hypothesis or a constant response, depending on the context that you're working in.